Okay. I think. Yeah. Okay. Cool. So the live stream's up right now. I'll share the link. Oh, whoops.
Yeah. Yeah, so we're once they rely on it, like they don't have the labor to do it. Okay. This is just a small. Okay. I see.
Strength length up. Cool. All right. Check the front door. See if there's still.
Okay. I don't have an adapter yet, so should I just?
The run guard.
Okay, cool. No problem.
Actually, yeah, if you don't mind. How about the very sure. 1B7B6C. Pi at the end of there, just like that. Okay. That's a pass. You just write that on the board.
Okay.
Is the door locked? At the front, like, did you come to the house? Alright, but is the door locked?
And so, I guess, more we can grow right? It's like higher stakes. Sorry?
It might be unlocked because I'm used to it being.
Yeah.
But,
Thanks. Yeah.
the question is sort of if you're thinking of a robot thing, I don't know how that can go. Ultimately, you can't have a robot or something, so it's like hard cap. So I guess it depends on the cost of the I guess really, I think probably not, there's no economic break for it.
Can I sit here? You're sitting by yourself. Was the door locked when you came in? Because that was unusual. Normally it's not locked. I couldn't, thankfully someone was reading it. I couldn't have come.
It locks at 6:30.
6:30, oh, so usually come in way earlier.
There are a lot of pretty bad things.
This is dedication, by the way.
What is dedication?
It's my big birthday today, and I'm. And then I was listening to the debate.
Presidential debate.
Right, I know,
On
that's
the
what I'm
way
thinking,
in.
there may be like
On the
adult
way in,
entertainment.
and then of course, I'm going to the whole story, but you know, so the one candidate goes, she says, it's my granddaughter's birthday today. No, it's not, it's a lie. I'm not. So I got my data in.
Somebody will get some money to get approved. wanted to say hi. Thanks for coming in.
Nice to meet you.
Nice to meet you too.
And did you want me to use the mic too?
There was supposed to be another guy to come down here now, but that.
Do you know where the GPI port actually is? Is that somewhere over here?
There's a.
So it's not like you're.
So are you working on something on this?
Actually, it should work, yeah. Okay, cool.
Okay.
Both sides of the.
Not exactly.
That one, yeah.
Actually, to get the accuracy.
And then I had a bunch of starting stuff. Well, my sister. So, almost out of madness.
This guy may have
Right, so we could go, thankfully I have all the background, it's not enough. Specialization, because I have a master's.
Oh, it should play through the room speakers. It should play through the room speakers.
Yeah, there should be a connector
So I
there.
had to go hold up on the sysadmin. I never was a sysadmin, but I knew enough about Linux, so. So you can't, like, can't do a whole lot with fighting hackers, like, that's the biggest fight right now. It's not my startup.
Well, maybe
There's actually a
It's
way.
like, I need to get some incentive. What is everybody else doing?
but, yeah.
That's a black hole.
There may be.
The last thing I can think about trying is plugging this into your laptop.
We kind of.
You tried that.
Oh, and what would that do? Just play my voice through the speakers?
Yeah, so unfortunately, I think the audio goes to the HDMI port.
Oh, I see.
It's one of the things, you know, these big companies put out a whole bunch of stuff about it. It's all
You wait the.
one way. I started scripting on my machine. Cats, like the signals. I'm like, I'm always building that like active spider detector. So I reinvented the but there's so much compute
And then having multiple shots.
as long as they work on the task. Otherwise,
You're hoping this will pick up my laptop's mic?
Yeah, if you want to open the spot, you can the sound.
you just get so this is not my electronics. Oh,
I don't know, maybe it's not.
I don't want to get yeah, that's smart though. You can make it hard, make it so difficult that they don't will
Yeah.
access.
All right. Well, we'll just have to go with.
I'll just be louder.
You know,
If you don't
not
mind.
even
Yeah, that's fine.
Sorry about
Just
that.
like your
Not a
phone.
problem.
It's really annoying.
So was somebody in the audience that wasn't hearing well enough, or was somebody in the live?
Yeah, it was a couple numbers in the audience. The live stream has trouble hearing other people's questions sometimes. So.
Okay, I'll try to remember the question guys later. Yeah, yeah. Okay.
So I noticed that they were going to-
Sorry.
Cool.
That's almost a week.
Great. Ah, thank you. Sorry about that. Yeah. Perfect. Thank you. Ah, thank you. An FYI, if you guys need help connecting to the internet as a temporary account we can use for now. And yep, that's good. Just slip in. All right, I think we are good to go. All right, go ahead, introduce yourself real quick if you need to, and
Okay.
we'll get started. Thank you.
Yeah, am I loud enough for everybody in the back? Okay, I'm Ian Goodfellow. I'm the first author of the textbook that we're all studying. And thank you for everybody who came out tonight missing the Trump versus Hillary debate. Our audience is a little bit smaller than usual. Tonight we're covering chapter 11, which is practical methodology, the way that we actually use all the different tools that we've been learning about so far. So what do you think drives success in machine learning the most? Do you think to be really good at using machine learning, you need to know a lot of really different obscure machine learning algorithms? A lot of people used to think that way. I feel like the last year or two, people have started to get better calibrated. That what's really a lot more important for success is having enough data and also really knowing how to apply a small number of techniques. So the choices involved in how to apply them are actually really important. It's not really possible yet to just take an algorithm and unleash it on a data set and have it do everything automatically. There's still really a lot of a human in the loop until you actually find the right recipe. And then the algorithm can handle things at test time, but there's still a lot of development work that goes into most successful machine learning applications. So I'll talk through how you build one of these. As a running example where I discuss all these different design decisions and how they were put into place in a real system, I'll use the Street View address number transcription system. I worked on this as an intern at Google, along with the rest of the StreetSmart team. The basic idea of the Street View address number transcription system is that it takes a photo with a complete address number in it. So it can have multiple digits rather than just one. And it runs the entire image through a single neural network, and that neural network outputs a complete sequence of digits. So the time that we did this, it was a relatively new approach. People used to use multi-component systems that would do things like segment the image into multiple digits and then have a classifier for each digit run separately. The main business purpose for this is to update the maps. That in countries where the maps do not already have good GPS coordinates for everybody's addresses, you can actually just take the photos from the Street View cars, take the GPS coordinate of the car when it took the photo, and update the map with the address number that the car saw at those coordinates. So, yeah,
Those
go for it.
examples there, have they already been, they look like they've already been clipped to focus on the memory?
Yeah, so I won't concentrate on this, but a pre-processing step for this pipeline is another convolutional network that determines where you should look generally. It's not precise enough to know exactly where the digit is. Part of the reason that I'm not talking about it is just that I don't know as much about the decisions that went into it because at the start of my internship, we already had a pretty good system for figuring out generally where the digits were. And I don't feel as prepared to talk about the history and all the choices that went into that aspect of the system. Yeah.
So usually on a street, the numbers will, of course, will be related to each other. Like usually they're increasing and they go up by, you know, all evens on one side, all odds on the other side. Did you take advantage of any kind of locality like that?
No, yeah, so the question was, did we take advantage of the fact that address numbers often are sorted in an increasing order as you move down the street? And we actually didn't use that at all. It probably could be used to get a few extra percentage points of coverage, but not every country actually has sorted address numbers. And a lot of the places that are the most difficult for us are also the places that don't have the sorting. Just also from the point of view of maintaining the database and keeping track of relationships between different address numbers, it would be a lot of extra implementation and software engineering work to know which houses were on the same street and like which order they should be increasing in, that kind of thing. When we use only the photograph, it's really easy to process things in really large batches and not worry about trying to process a whole street at the same time. And not worrying about needing to make batch sizes of examples that can fit a street exactly.
Is that only for numbers?
So the question is whether this is only for numbers. In this particular application, I believe that we did numbers and letters, but not dashes. So some people have an address like 3A or something like that if your house is, you know, like part of a unit. And if I remember correctly, we were able to handle that in this particular application. Also, nothing that we did was really hard-coded for numbers. The question is mostly just which training data do you have ready, and do you have enough of it that you won't overfit when you bring in more character classes. But in theory, everything is applicable to any kind of character.
Last question, were there examples of this being built on top of another network? Something that the problem was already solved, or maybe this being used in some other problem later?
So the question is whether there are any examples of this being built off of another network or this being used to solve another problem later. So once you have anything that can do optical character recognition, you can plug it into solving lots of other kinds of problems. You could imagine that maybe you're building a reinforcement learning system and its goal is to get to a particular address, and then you could read the address and tell when you've gotten there. I don't know of anyone actually doing follow-up work that had this as a component of a larger machine learning system. Obviously, it's part of a product at Google, but the most important things that come after this are not machine learning, but just incorporation into traditional database software.
Because reuse is a good thing to have if possible.
Yeah, you could imagine that maybe there's a lot of machine learning going on in terms of analysis of the map data, and in that sense you could say that this provides some of the input to the next step. But there's not anything really tightly integrated, like a machine learning model that, there's not anything like a machine learning model that has like an eyeball that it can turn around and aim this at address numbers at will or anything like that.
Okay. The chapter said that there is, that they use some machine learning solution to find the digits in the first place.
Yeah, so it's very, the comment is that we use machine learning to find the digits in the first place. So that's what we were discussing a minute ago, that these images are relatively small. I forget their exact size, maybe 256 by 256 or something like that. But they're extracted from very large, high-resolution street view panoramas. And it would be very expensive to run the convolutional network across the entire panorama. So mostly to reduce the computational cost, we had a simpler system that chooses the small image to process before we bring in the very detailed convolutional network.
Is there anything interesting to note about that?
It's difficult to discuss because that part of the system has not been published, partly because the people who worked on it weren't interested in publishing it, and partly because that part was less scientifically interesting. And just because it's never been published, it's never been approved for release and public discussion. So it makes it harder for me to say exactly how it worked. The answer is there's a lot of things you could do that would do an acceptable job of doing this first step. And the specific choice of what we did at Google is not all that interesting because there's so many different things you could do that would actually more or less work for this part of the pipeline. Okay. So the overall process for building a really successful machine learning application is a three-step pipeline. First, you need to actually plan what your goals are, and you should be able to specify those goals quantitatively. You'll need to choose what kinds of metrics you're going to use, and also what values of those metrics you need to achieve for your product to be viable. The second step is to build an end-to-end system as soon as possible. Just get the system working and not try to predict too much which part of the process will be difficult. Just build the entire thing and then start to measure which part doesn't work. And then the final part of the process, the one that usually takes the most time, is data-driven refinement. So you've already built your system and you're testing it out, and you use actual test results to figure out which parts you should change and how you should change them. The most important part of machine learning methodology is understanding which kinds of changes you ought to make, rather than just blindly changing things and hoping that they'll work better. So the very first step, where you set your goals, requires you to identify the needs for your product. For example, some products might not need very high accuracy. Other products might need really high accuracy. So for example, if you're going to make a surgery robot, you want that to be really, really accurate because you don't want to slice into somebody's aorta or something like that. It's a mistake that would be hard to fix. If you're making an app that's just meant to entertain people on their phone by saying which celebrity you look like, then it's probably okay to have some lower accuracy. And mistakes might even add to the entertainment value in some cases, just if the mistakes are really funny. In the case of the Street View address number transcriber, we fell closer to the high accuracy requirement. So it's not as high stakes as a surgery robot, but the utility of the product only really exists if it's reliable. If you want to get turn-to-turn voice directions to an address and your phone leads you to the wrong house, you're probably not going to be very happy about that, and you might not use the product again. So we made it a very high priority to only add address numbers to the map if we thought that the transcription was as accurate as if a human had done it. The next step that you should do is to choose the kinds of metrics that you're going to use. And these are actually very important. You might think that accuracy covers pretty much everything that you might care about, but actually accuracy can be an almost meaningless metric. For example, I could tell you that I'm able to diagnose HIV with roughly 99% accuracy. And the way I do that is I just tell everybody that they do not have HIV. Because it's a rare disease, I'm right almost all the time. But clearly I'm not actually providing any kind of useful test. And anybody that does have HIV is getting the wrong information from me. So for situations like classification problems where one category is rare, you need to use specialized metrics. So for rare classes, the metrics that we're usually interested in are called precision and recall. Precision is the number of times that we say we've detected the rare thing that it's actually there. And so my example test where I just tell everyone that they don't have HIV would actually not really have a precision value because I would never return a positive number. So that percentage would be undefined. The other metric for this rare class situation is recall, which is saying, out of the objects that you ought to detect, how many of them did you detect? And that's where you can see that my hypothetical HIV detector is a really bad idea, because it gets 0% recall. It never returns a positive at all. So both precision and recall, you'd ideally like them to go up to 100%, but it's often difficult to achieve that. Another metric that's interesting to measure is coverage. So coverage is the percentage of the time that you are able to actually provide a response. You can actually make machine learning systems that just give up and say that they're not going to give an answer. And if they do that in cases where it's more difficult to process the input, they can increase their accuracy on the remaining examples. So that's what we did with the Street View address number system, was we decided to trade accuracy for decreased coverage. Essentially, if we gave up on a small percentage of photos, we could be sure that we were able to reliably transcribe the remaining ones. And we were actually able to give up on transcribing some of them without losing too much coverage on the actual map for two different reasons. One is that we often had more than one photo of the same physical address number. So if the car took 5 pictures of the same building on the way past, and we had to give up on 3 of the 5 pictures, we could still actually locate it using 2 of the remaining pictures. The other reason that we were able to give up on some photos was that we can actually just pay human operators to transcribe the really difficult ones. And as long as we significantly reduce the burden on human operators, it's still cost effective. So that was the approach that we took in order to actually get really, really high accuracy. And we actually got above the accuracy that an individual human rater would have. We were able to get accuracy rates that were more like what you would get if you had 5 human raters vote on what a difficult transcription should be. There's also all kinds of other tasks besides just transcription and classification. So like regression, where you predict a numerical value. Those kinds of tasks have other kinds of metrics, and you need to think about which ones are the most appropriate for the task that you're working on. Does anybody have any questions about metrics?
I was wondering how human precision was evaluated.
For the Street View task specifically?
Yes.
Yeah, okay, so the question is, how did we evaluate human precision? And in this case, it was really human accuracy, to be really pedantic. We looked at the rate at which different humans agreed with each other, and we assumed that after we had several humans transcribe the same input, that the majority vote would be correct. And we just looked at the agreement rate of the individual people who disagreed with the majority.
I have a question. How did you decide when to give up on a particular image?
Oh yeah, so the question is, how do we decide when to give up on a particular image? The basic idea is that the classifier is probabilistic. It gives us a probability of a sequence of digits, and we can look for the sequence that has the highest possible probability. If that probability is below some threshold, then we give up and say that we have too low of confidence in our most likely transcription. So if your most likely transcription has probability 99%, then it's probably safe to return it. If your most likely transcription has probability 30%, then you realize that maybe there's an ambiguous digit somewhere. Maybe one of the numbers fell off the house, or maybe there's a bush in the way of one of the numbers, something like that. Something is obviously making you be really uncertain about what at least one of the digits should be. Oh, and those are both real things that can go wrong, like digits falling off, things like that. After you've chosen your metrics and your goals that you want to work toward, the next step is to build an end-to-end system as soon as possible. So what I mean by an end-to-end system is a system that solves the entire task that you care about. The reason that I specify that you should actually build an end-to-end system is that a lot of the time people make a prediction about what they think will be the hardest step of some pipeline. And then they come up with a lot of metrics to measure how well that step is doing. And they spend a lot of time and engineering effort developing just that one stage of the pipeline. And then maybe once they get it perfected, they go to build the other steps, and it turns out that one of the other steps is even harder. Or sometimes it turns out that they spend a lot of time optimizing something that didn't actually need to be really, really powerful, because other steps are able to compensate for it in some way. So for example, with the Street View address number transcription system, our pipeline included transcribing address numbers, but it also included looking at multiple different photos of the same physical object and seeing if we had been able to transcribe at least one of those. So we could have spent a lot of time trying to squeeze really high accuracy and coverage out of the transcriber. And then at the end of the day, we could have found out that because we have multiple views of each object, we had actually been wasting our time optimizing too much. By building an end-to-end system early on, we were able to make sure that we actually had a good idea of how all the components perform together, so we could spend our time in the right places. The basic idea here is just to build the simplest viable system you can think of. And usually that takes a lot of domain knowledge in order to know what you ought to do. It also takes, sometimes a lot of intuition and luck. Like in our case where we used the single neural network to transcribe the whole sequence, I believe that was Yaroslav's idea. And we were all kind of skeptical that it would actually work. We decided that it was a low effort thing that we could try, and if it didn't work, we could fall back to using a multi-component machine learning system. And then it worked. So in that case, Yaroslav's daring bet paid off. But in other cases, you might build your end-to-end system and find out that one of your daring bets didn't quite work, and you need to go back and spend more effort at that step. So in general, how can you decide what your basic architecture should look like? One thing you can do is you can find a publication about how somebody else used machine learning on a similar task, and you can copy their architecture. So if you want to make some kind of object recognition system, you can copy the architecture from a recent ImageNet contest.
Yeah.
Yeah.
Are there any like blogs or anything on like online resources or people that you kind of like check on or look to for inspiration in terms of like copying the state of the art? Like perhaps a Kaggle blog or some sort of machine learning blog?
I don't know. Yeah, so the question is whether there's any particular blog I look at for finding the state of the art. There was an effort at making a database that tracked the state of the art on several different tasks. And as far as I know, the author of that database doesn't maintain it anymore.
Okay. So you look to like actual papers from like ArcSiv and such?
Or I know which people to ask.
Okay, fair enough.
So for example, if somebody wants to know a really good architecture for a language modeling task, I might ask like Rafal at OpenAI.
Sure.
If it's something like generative modeling, I probably just know it off the top of my head.
Okay.
If it's something like computer vision, then I'd ask a completely different person. Unfortunately, there's not really one standardized, centralized machine learning encyclopedia or blog that really covers a wide variety of state-of-the-art results in everything. The different research communities like reinforcement learning and natural language processing tend to be somewhat isolated from each other. So probably the biggest decision you should make when choosing your model architecture is whether to make it deep or not. Obviously, we're mostly discussing deep architectures here because this is the book on deep learning, but even I am not going to tell you that you should always use deep learning. A lot of the time, something like a Bayesian method might be the most appropriate, or something like a shallow model trained with more or less the same techniques we use to train deep architectures might be the most appropriate. So what are the main considerations for deciding whether you should use deep learning or not? The first one is the amount of noise and the amount of structure that your data has. Deep learning is useful because it allows us to describe really a high amount of structure. And we do that by having all these different layers that are composed together to understand all the different ways that simple functions interact to form very complicated functions. If the structure in your data doesn't actually require a complicated function to describe, then there isn't really a payoff to using all that extra machinery. And it might be worth it to just use something that you can fit easily with convex optimization, where you know that you're reliably going to get an optimal result in a short amount of time without needing to do too much hyperparameter search. Also, if there's really a lot of noise, deep learning is usually not going to give you very much of an advantage, because even if there is a lot of interesting structure, generating the data, the noise might be large enough to hide that structure and just prevent you from learning about it. Or if you have very few training examples, it's likely that a Bayesian approach will perform better than a maximum likelihood approach with a complicated model. And so far, we don't have truly excellent Bayesian deep models. In the long run, I think that we will have really good Bayesian deep models. And this will no longer be a reason to use deep learning or not deep learning. It'll just be a reason to use Bayesian deep learning or maximum likelihood deep learning. Okay, so suppose that you decide that your data is really noisy and doesn't have a lot of structure, or you don't have enough training examples to train a deep model. Then you need to choose which actual baseline you'll use, which first model you'll try when you use your shallow model. My first recommendation would just be to use the model that you're most familiar with. There's lots of different shallow models out there that are perfectly good. If you are really used to using random forests, then you're probably going to do really well applying random forests. And if you read something that makes you think that like an SVM is probably the best thing to use for this task, but you're not used to using SVMs, even if SVMs are objectively a little bit better for this particular task, you're probably better off going with the algorithm that you know that you'll be able to apply really well. And there's lots of algorithms that are perfectly good. Logistic regression, SVMs, and boosted trees are all really good. Gradient boosting is really good. Okay, but suppose that you decide that you do need a deep model, that your problem has plenty of training examples, there's lots of structure, and there's not enough noise to hide that structure. Then you need to choose the general architecture family that you're going to use. So by architecture family, I mean, do you want a fully connected network, a convolutional network, a recurrent network? And then within those families, there's finer detailed architectural choices you can make. Within the family of convolutional nets, you can choose if you want an inception model or a ResNet or whatever. The basic idea is that the type of data you have will tell you which architecture family you should be looking at. If your data has no particular structure to it, if it's just vectors of measurements coming in, then you probably want to use a fully connected network. If you have some kind of spatial structure to your input, like it's an image or it's a spectrogram or it's some kind of measurement that was collected on a grid, then you probably want to use some kind of convolutional model. You might possibly want to use a recurrent model, but usually the convolutional one would be easier to deal with. Then if you have some kind of sequence structure where there's causality especially, and you have information flowing through time, or flowing from the start of a sentence to the end of a written sentence, then you probably want to use the recurrent network family of architectures. So let's say you've chosen to, oh yeah, there's a question.
Is there a lot of work on like a graph structure, like for example, a tennis match outcome? Like if you want one player versus one other, how would you model that?
I see. Okay, so the question is if there's a lot of work on graph structured inputs, and specifically, how would you handle matches between different tennis players? So that field is not especially well solved, as far as I know. There's some work, I believe, from Harvard, I think from Ryan Adams' lab, about processing molecules. I think the basic idea is that it's something like a recursive autoencoder, where small neighborhoods of the graph can be encoded, and then you look at the way that those graph neighborhoods are connected to each other, and you apply the same encoding operator again and again recursively until you have a summary of an entire graph. That's a way of making like a classifier that can tell you what the properties of a whole graph are. And then if you want to know like how two tennis players would do against each other, that seems like an easier problem than the general problem of operating on graphs. You could just do something like have one vector representing each player and just train a classifier that takes two vectors as input. And you could just concatenate them together and use a fully connected network that way. You might need to do things like make it invariant to the order in which you present those two players. So for example, you could train it with player A versus player B, and then player B versus player A, and then you report the same outcome both ways. There's a paper by Oriol Vignals and some of his collaborators called Set to Set, where it's about models that read whole sets of inputs and then produce sets of outputs. And I don't remember exactly how it worked. I don't remember exactly what their conclusions were. I think they did something like take a sequence-to-sequence model and just shuffle the order of the members of the sequence. And your example with the tennis players would be a two-member set, essentially.
Yeah, you could, this is a fairly complex problem, but you could easily imagine spatial and sequential combined. Like that thing moves like a cat, or is there work on that out there?
Yeah, so the question is whether there's work on combining spatial and sequential. And yeah, there is a lot of work on modeling video, or on classifying video. That's been held back to some extent by there not being very many labeled video classification data sets that are very large. And generating videos is just really, really hard. There is some work on that with things like generative adversarial nets, but the results are usually not very good. Currently, video generation usually has one of two problems. The most common problem is that the predicted video just becomes extremely blurry as you go forward in time, that essentially after a while all pixels have a very Gaussian distribution if you don't know the joint distribution really well, if you just look at the marginal over any individual pixel. So you'll just predict the mean of that Gaussian and things will just sort of blur out to gray. Then if you use approaches that are more based on generative adversarial nets, or based on predicting both the values of pixels and the values of derivatives of pixels, then you're forced to actually make images that have sharp edges and things like that in them. And those, there isn't really a good technical term for it. They often just look really weird. There's a project that was released recently showing generation of images with generative adversarial nets, or generation of videos of generative adversarial nets, and there's videos of like, there's a picture of a baby and the baby's head just like grows and swells like a bubble gum bubble or something. It just looks really surreal. In terms of the architecture, the way that these usually work is you make them convolutional across space and recurrent across time. So you learn a way of updating your prediction from one frame to the next, either going straight from pixels at time t to pixels at time t+1, or using some kind of latent code at time t and then going to time t+1. It is also possible to be convolutional across both time and space, but that usually messes up the concept of causality. There's also models that use convolution across time and just make sure that the kernels are positioned in a way where they can't carry information backwards. So like WaveNet, DeepMind's speech generation model uses these masked convolutions that can only see backward in time.
Sorry, what was the name of that one?
That's called WaveNet.
WaveNet?
Yeah, because it generates audio waveforms.
Yeah. They have a very interesting post on their website for it.
So let's say you've decided to use a fully connected model, just a traditional deep feed-forward network. Now you need to decide what's a reasonable default that you could use for your first attempt at solving the overall task you're trying to solve. Well, the first thing that you should try is probably something that has 2 or 3 hidden layers in it. If you have fewer than that, then it's likely to not actually have very much expressive power, and if you have more than that, it might be difficult to optimize. You should use rectified linear units as the most sensible baseline, and in some very rare cases, you might move away from those later on, but there are specific tests that you can run that will suggest that rectified linear units are having a hard time. Usually the test is just, you'll see that you're getting lots of zeros you're getting units that are stuck being 0 all the time. You should basically always use batch normalization, unless you have some really specific reason not to. And for the optimization algorithm, you should probably use Atom. Depending on whether you expect that you'll have a lot of underfitting or a lot of overfitting, you may or may not want to use dropout. So basically, if you're going in with just a few thousand examples, and it's a difficult, complicated task, then you can probably bet that you're going to be underfitting a lot. So you use dropout. If you have more than like 15 million examples, then you can probably start to bet that underfitting rather than overfitting will be your problem. And then you probably want to start without dropout. Either way, you should be prepared to reverse your choice based on tests that you run later on. So that's the fully connected model family. Any questions before we move on? Okay, so let's say we're using a convolutional network model family. In this case, there's so much published that it's really pretty easy to just go out and find a good network that you don't even need to copy the architecture. You can probably just download a completely trained network. So in a lot of cases, you can just take somebody's model that was trained on ImageNet and you can actually use the features from it for other tasks. And you only really need to retrain the output layer. So that really saves you a lot of work and gets you off the ground really fast. If the task you're doing is farther away from regular object recognition stuff, then you might just copy the architecture for an object recognition task and start training it. Or if you really don't want to read a paper and you just want to dive in and do something simple that will usually work pretty well, just make a deep residual network. Use batch normalization and use Atom to optimize it. That's just a really simple baseline that's pretty much always going to work for you. The last major model family is the recurrent network model family. And the baseline here is also pretty straightforward. You should use an LSTM as the default model. You should train it with stochastic gradient descent. A lot of the time it's not really as important to use something like RMS prop or anything like that. Even just normal gradient descent can often work quite well. One thing though is you should definitely use gradient clipping. It's because recurrent networks are prone to suffer from the exploding gradient problem. And gradient clipping will just, shrink those exploding gradients for you so that learning will stay stable. The update steps you make when the gradient explodes won't be especially useful, but they'll at least be stable enough that they won't ruin your model, and you can, cling to good performance long enough to start seeing some smaller gradients. Also, the LSTM has a forget gate, which is a sigmoid unit that we multiply by the state. And when it's close to 0, we forget what that state was containing. If we multiply it by a lot of these forget gates that are close to 0, then we have a big problem with vanishing gradients. So one way to make sure that we don't have the gradient vanish too much early in learning is to set the bias parameter for that forget gate to some kind of high value. So if you set it to +1, then the forget gate is also going to be pretty close to 1, and it will more or less propagate information. Over time, the model will start to learn to shut off that forget gate a lot of the time to take it closer to 0, and then some gradients will start to vanish, but only in places where the model had already more or less decided that it ought to forget some things, so it won't be too harmful. Does anybody have any questions about the recurrent network model family? Okay. Oh, yeah.
So when you have the forget gates, you put the you don't use ReLU units to forget stuff, right? And with sigmoids and 10H, we usually get into the problems of vanishing gradients. Was there any work done on forget gates to not have those problems?
So in principle, the question is, you don't use ReLU units for forget gates, and then other things like hyperbolic tangent and sigmoid tend to have more trouble with vanishing gradients because they have a hard saturating value. So is there any work on solving that particular issue? So you could possibly use a rectified linear unit as something like a forget gate. I've done it in deep feed-forward architectures, and it works okay. In really deep recurrent architectures, you tend to get a problem with exploding activations if you have rectified linear units. That a rectified linear unit will see big activations in the previous layer, and it'll come up with even bigger activations, and the problem just compounds over time. So that's why we usually use something like sigmoid or 10H for these recurrent models. We've more or less gotten rid of those units for the other model families. In a lot of cases, it seems like LSTMs work pretty well, even though they're using units that would usually saturate too much for feed-forward models. But one thing you can do to make them work better is layer normalization. So layer normalization is a lot like batch norm, but it has been adapted for the recurrent model family. And because it keeps the activations in a relatively sensible region, it reduces the amount of them that saturate really strongly and lose the gradient. Other than that, there isn't a whole lot of work. There isn't really anything that's, like for example, there's not an optimization algorithm that's designed to deal with the saturation. There are lots of optimization algorithms that intend to do that, but none of them work very well so far. So the third step of the overall model development pipeline is also the most labor intensive and usually lasts the longest. Especially after you've built up a lot of experience building models, you'll often have like your own personal library of little model pieces that you can slap together really fast. And so you'll get your initial baseline up within a day or two, but then it might take several months of tweaking to get good performance out of the final model. So the basic idea of the data-driven adaptation stage is to really focus your decisions on actual measurements that you make, using data to target the changes that you should make. You shouldn't buy into hype. Like if some new algorithm comes out that people are really excited about and you've been hearing that it gets great results, you probably shouldn't just switch to that model because you've heard that it works really well, unless you have some specific reason to believe that that model is fixing a specific problem that you're getting in your task. The most important things you should measure are the training error and the test error. There are a lot of other things you can measure too, but these are really the bread and butter that will identify 90% of the problems that you're likely to encounter. And when you measure train and test error, you're thinking about diagnosing overfitting and diagnosing underfitting. And all the changes you make should be based on which of those problems you think you have. So if you measure your training set error and you find that it's really, really high, that means that your problem is essentially underfitting. And that gives you a whole set of different problems that you can look for to address the underfitting problem. Now most people, when they hear underfitting, they immediately start thinking that they need to make their model bigger, or they need to make their optimization algorithm smarter, or that kind of thing. In practice, it can actually be a problem that has nothing to do with machine learning technology. So one of the very first things you should do is you should start to inspect your data for defects and make sure that you haven't just prepared the data in a way that it's impossible to solve the task. Like for example, maybe you shuffled the input examples, but you didn't shuffle the labels. So you're trying to train your model to map inputs to random labels. That's actually something that happens kind of a lot. Another thing is you should check your software for bugs. That also happens quite frequently. Even if you're using something like TensorFlow or Theano, even published libraries maintained by lots of people have bugs that can hit you if you do something unusual. Like for example, recently I had some trouble with second derivatives in TensorFlow. We're not actually using the correct formula. And that had just been overlooked because most people only use first derivatives. If you get really high training error and you're using your own software for a lot of things, you should maybe think quite a lot about whether it's worth the time it would take to make sure your software is free of bugs. Because unless you're doing something very specialized, it's probably not worth the time to build your own system. And you should just use an off-the-shelf one where the rate of bugs is much lower. if you do decide to try to remove all the bugs from your own software, there's a lot of advice in the book that's more detailed than I'll go into in this talk. But basically, that's the road that you're headed down if you decide to build your own. The next thing that you should do once you've ruled out the non-machine learning related stuff is to tune the learning rate. So before you start trying to improve your optimization by using really fancy optimization algorithms, you should make sure that you've just configured the one that you're using really well. And there are a few other optimization settings that can matter a lot. If you're using momentum or something momentum-like Atom has parameters that are analogous to the momentum parameter, you should configure those too. There's other things like the decay schedule for your learning rate. You usually want your learning rate to shrink over time, so you can try to adjust those. But usually the absolute most important setting is just the learning rate itself. And you can just do a very coarse search where you do kind of a binary search for a good value of that learning rate. And that will be probably the thing that has the most effect on the optimization that you do. You can continue to squeeze more percentage points out from focusing on the other aspects of the optimization algorithm, but the learning rate is really the biggest one. And then finally, after you've done all of these other steps, if you're still having really high training error, you should make your model bigger. And if you're able to, you should probably mostly do that by making it deeper. But you should do all of these things before you start working on really complicated optimization algorithms, before you start a research project on how to do second-order optimization with line searches or anything like that. You should usually not conclude that your problem is just fundamentally harder to optimize than anything anyone else is doing. You should assume that a good learning rate and a big model will be most of what you need to get the task done. So when you check the data for defects, that's probably the first and most important step of debugging high training error. What you're really trying to ask yourself is whether a human can process it, if that's appropriate for the task that you're doing. A lot of the time when we're doing AI-style tasks, like natural language processing, object recognition, that kind of thing, we do expect that a human can process this kind of data. And so you should actually visualize it to the extent that it's possible, instead of just relying on metrics. A lot of the time, a bug in a metric can be really devastating because you can actually mislead yourself into thinking you're doing well when you're not. Everybody has had an experience where, one day they thought that they were getting the state of the art on some task, and then they realized that their evaluation code was wrong when they tried to visualize, the bounding boxes around the objects they thought they were detecting or something like that. And you saw that the actual visualization didn't make any sense. So in the case of the Street View address number recognition system, the single step I took that increased the accuracy the most on the whole project was I made the images bigger. We had a two-stage system where the first stage would say where the address number is, and then crop a small image surrounding that address number. And then we would run the transcription system to read all the digits out of that small image. Well, early in the project, I realized that we were getting high training error, and I started attempting to diagnose what was causing it. I found out that a lot of our mistakes were actually cropped too tight and were missing some of the digits. So here's an example of an image where we can only see a 6624, but the ground truth label is 26624. The human who labeled this was able to see the larger photo and had enough context to label the whole thing. So the way that I solved this was not anything to do with machine learning, it was just a change to the data collection pipeline. I just made the images wider, and that was sufficient to deal with the detection network underestimating the width of the digits sometimes. After we were able to actually see all of them, we were able to transcribe them really well, even though we had to deal with the extra issues of seeing more of the image. I mentioned that one of the main things you can do to increase, solve the problem of high training error is to increase the size of the model. And that to the extent you're able to do it, you should probably do it by increasing the depth of the model. Here's an example from the Street View project where we measured the test set accuracy for several different model sizes. We found that as we increased the number of hidden layers, the test set accuracy kept going up. And this was back before there was batch normalization and back before there were residual networks. So it was hard to keep pushing this to greater and greater depths, because eventually optimization became difficult. Today, you can easily push this much further using things like those techniques I just mentioned, and also deep networks with stochastic depth. So let's say that you have a problem with the test error being too high. Well, that means that you have a completely different set of problems that you need to deal with. First off, there is still a possibility that you have a software bug. For example, if you need to save the model after you're done training it and you reload it at test time, it's possible that you're just failing to serialize and deserialize the model correctly, and that's why your test error is high. So you should still think about bugs, but they're actually much less common in this setting. Usually when you have high test error, it is actually a problem related to the machine learning itself. So the simplest thing that you can do to reduce the test error is to add data set augmentation. This is something that you don't usually read about in machine learning papers, because researchers who write papers usually don't like to compare their method to data set augmentation, because it's a method that requires a lot of hand design, and it's not a method that involves solving the underlying machine learning tasks. But it is the method that will get you to good performance the fastest and usually with the least effort. You do need to think a little bit about what kind of invariances there ought to be in your data. But if you're working with something like images, then you know right off the bat that things like translation invariance or contrast invariance, lighting invariance, invariance to noise added to the image are all really important things. You can just start adding all those transformations to your data set and get a really big improvement. Another thing you should definitely do is add dropout. That's a really good regularizer that's really low effort to use and very rarely causes any significant problems. The dropout is also a special case of ensemble methods. So ensemble methods are also really, really powerful. Sometimes if you're already using dropout, an ensemble of models trained with dropout is not really that great. It won't improve that much over the individual model, but it still does sometimes, and it's worth trying. And if for any reason you're not using dropout, an ensemble is also a really good idea. Also, the results for this year's ImageNet object recognition contest just came out today. And as is usually the case with most contests, the model that won was an ensemble of 6 different models. So if you're able to pay the cost of running multiple models at test time, ensemble models are a really good way of reducing your test error with very little engineering effort, apart from the effort needed to make the models actually run. The other thing you can do that you don't usually read about in machine learning papers is that you can collect more data. So usually machine learning papers are written to perform on some benchmark, and the benchmark is defined with some number of training examples. So you don't see many machine learning research papers talking about how well you can do if you just add a lot of data. But if you're interested in solving the problem and not in making the world's most beautiful machine learning algorithm, adding more data is essentially the most straightforward path to success that you can have. The only real question is how expensive it is and how much you actually need. One thing you can do to decide whether you ought to gather more data or not is make a little plot where you see what your test accuracy is if you train with different subsets of the data you already have. So if you see that when you train with half the data you currently have, your test set error goes up by like a factor of 4, then you see that there's actually quite a lot of value derived from the last time you doubled the size of your training set. And then you can think about how much it would cost to double your training set size again, and if it would be worth it if that cut your test set error in half again. Yeah?
So one problem with collecting more data is often labeling the data. And I know, like, from a machine learning background, there's a field of research called active learning, which tries to identify which data set, examples to label. But I haven't heard of active learning being combined with deep learning much.
I submitted a paper to a workshop about that today. I was using active learning as like one step in a larger pipeline where, I mean, I guess you'll see soon enough, but it's a paper where we're not allowed to use very many labels for a reason other than just the effort of collecting them. And I don't actually know of very much of an active learning literature for deep learning. You're right about that, as far as I know off the top of my head. What does seem to work pretty well is just running a lot of training examples that don't have labels yet through your pipeline and seeing which ones get really low confidence. And then you label the ones where your model isn't confident. It doesn't really seem like the perfect approach because sometimes your model might have low confidence just because an example is really difficult to process, but not because there is ambiguity about which label should be there. Like if you have a really blurry image or something like that, that's going to have low confidence, and it would still have low confidence even if something similar to it had been labeled. There's also, I imagine that you could probably write down something like the optimal Bayesian schedule for which examples to label. Like a lot of the hyperparameter search algorithms based on Bayesian optimization have different criteria for which sets of hyperparameters they should try out next, based on the expected improvement they'd have. You might be able to do something like that for active learning. I'm just kind of speculating now. We don't know the specific paper in the literature out there. So you can make graphs of how your performance changes with the training set size. And there's a few different things that you can notice on these kind of graphs. In the left, I make a graph of the error of a few different models. One thing we can see is that there's an error rate called the Bayes error that I'm highlighting with the cursor here. It's the dotted magenta line. And that's just the error that you get if you actually know the true distribution that the data is drawn from. Usually that error is greater than 0 because there's some kind of noise in your data. Then you can look at the way that different models actually perform. Like if you have a model that has some kind of fixed capacity. So we use the blue curve and the green curve to look at the train and the test error of a model that's just a quadratic predictor for this regression task. Yeah, question back there.
Yeah, how would you get the Bayes error for a data set?
So the question is, how do you get the Bayes error for a data set? Usually you can't, just because you don't actually know that distribution. To make this graph, I set up a synthetic task where I generated random data from a system where I specified the probability distribution. And that way I'm able to show the way that your model gets really close to the Bayes error over time. But in real life, you never really know if you're there yet or not. And it's always possible that some model that's smarter than us could actually get less error somehow. So if we look at the quadratic predictor, its train error actually goes up over time. It starts very low, and then it goes uphill until eventually it gets near the Bayes error. So what's going on there is that the model isn't able to memorize or able to fit more and more examples very well. And so as you collect more examples, the train error has to go up. But the test error goes down because you're reducing the amount of overfitting that happens. Another thing you can do is you can actually adjust the capacity of the model for every different size of training set that you try out. And in that case, your training set error is usually going to stay pretty low, and your test error will just consistently decrease over time. And it should eventually converge to very close to the Bayes error rate. If you have a model of fixed capacity, you're not going to get all the way down to the Bayes error rate. Instead, you'll get down to the level that your model's capacity allows. The other thing that's interesting is to look at the way that the model capacity changes as the number of training examples increases. So in the plot on the right, I actually show the degree of the polynomial that did the best on the test set at each of these different sizes. Well, there's error bars here because I regenerated the data set and reran the experiment many times to get confidence intervals. Part of what I wanted to convey with these plots is just that there is noise in this whole system. Like, you can't expect that if you add more training examples and retrain your model, it's definitely always going to do better than the last one that you trained. But there's this general trend that as you add more training examples, you're usually going to do quite a lot better. And if you make a really big increase in your training set size, then you can practically guarantee that you're going to do really well. Yes?
So isn't it weird that the training optimal capacity error rate is close to 0?
So it's turning out that it works better if it memorizes some of the noise. It is a little bit surprising, but that's pretty consistent with what we usually see. Until maybe about 5 years ago, people were really concerned with the idea of keeping models small to avoid overfitting. And now it seems like we actually do a lot better if we make them big and just regularize them.
Oh, real quick, one of the streamers, this is going back to a few of the slides.
Yeah.
One of the streamers,
which slide should I go to?
I don't know specifically, but it has to go back to just neural network structure. One of the streamers is asking if you increase the hidden layers a lot, what kind of problems do you usually see or can happen?
Okay.
Yeah.
Yeah, so on this slide, I recommended only having 2 to 3 hidden layers. If you have more hidden layers can help you to fit a difficult, complicated problem where your training error is high. So if you do see high training error, you should definitely add more layers. But when you first start a new task, it's usually a lot easier to fit a shallow model. If you have a really deep one, then you can have things like the exploding gradient problem. You can have things like the vanishing gradient problem. It can just be hard to find a good initialization for all your different parameter values. A lot of these things are reduced if you use batch normalization. So if you're using batch normalization, the recommendation to use 2 to 3 hidden layers isn't nearly as important as it was a few years ago before batch norm. But it's still just generally a higher probability that your configuration of hyperparameters is going to work out if you have fewer moving parts. Most of the benefit of having a deep architecture comes when you add the first hidden layer. That's when you go from having just a linear model to having something that can be a universal approximator. And after that, you get diminishing marginal utility with every additional layer. So if you have something like 10, then you have a lot of chances to screw up a hyperparameter, and you don't have a whole lot more benefit to the model complexity than if you just had one hidden layer. Once you actually start tuning things a lot and being careful about your hyperparameters, something very deep will probably work the best. But if you want to just do something quick and dirty and have it more or less work the first time you run it, fewer moving parts are always the most likely to just work without any fiddling.
Oh, and just a question for me: do you have anything in the book written about that, or like that pertains to like ResNets and such? Do you plan
I
on
believe
adding
there's
it?
nothing about ResNets in the book.
Okay.
Because so I think ResNets won the contest in like November 2015.
Yeah.
Or September 2015, and we were down to the point where we were mostly just editing content that was already there.
That's fair.
Yeah. One of the drawbacks to writing a textbook rather than writing a research paper or a blog post is that there's really a lot of latency in preparing an 800-page printed document. And so it's always going to be somewhat out of date.
That's fair.
Like in a book, you have to take on different goals.
And out of curiosity, do you have any plans for like a second edition or anything like that?
Well, there probably will be one, but there's
Okay.
not a concrete plan for
That's
it yet.
fair.
Yeah. So I was
Right there. Yeah.
Yeah. Okay, so one of the most important things you can do for any application is just tune the learning rate really well. This is an example of what the training set error looks like as a function of different learning rates. And this is after I've trained a model to completion. This is a small model that I could just train using NumPy and actually run lots of different experiments to give you a nice smooth curve. I don't remember off the top of my head what model this was. I think it was probably something small and shallow. It might even have been convex. If you make a curve like this for something like a convolutional network that's actually really expensive to train, it's going to look much more jagged than this. Usually what you see is that if you train for a specific number of steps and the learning rate is too small, you'll get high training error just because you didn't make enough progress before you had to quit. And if the learning rate is really small, it might be a very, very long time before you actually get the training error to go down very much. As the learning rate gets bigger and bigger, you get lower and lower training error. But eventually you get to the point where you start to inadvertently go uphill because your learning rate is too large compared to the curvature, the positive curvature, the positive eigenvalues of the Hessian for the optimization surface that you're working on. And then the error starts to go back up, actually very, very quickly as a function of learning rate size. On larger, more complicated models, this rightmost part of the curve actually looks a lot more jagged and random than for this relatively simple task. So here, it's almost like a step function where it just shoots up to some very high value as soon as you get too large of a learning rate. In practice for very large complicated models, you'll actually see a kind of random but more or less uphill pointed worsening of your training set error once your learning rate starts to get too big.
Sorry, is this with first order or second order gradient vectors?
Oh, this is with first order. There's not really much second order that's actually useful for deep learning so far, unfortunately.
So that's like the second order error.
No, it's just the value of the cost function.
I mean, like, this like, I thought like, you run into that problematic term once that second order term starts to get.
Oh yeah. So once the second derivatives are very positive compared to the learning rate, that's when you slam into this wall over here. There's a lot of different hyperparameters that you have to set besides the learning rate, and you sort of need to reason about each of them on a case-by-case basis. The basic idea is to think about what they do to the effective capacity of your model. So if you have a hyperparameter value and you increase it, is it going to increase or decrease the effective capacity of your model? So for example, the number of hidden units, it's pretty clear that's going to increase the effective capacity of your model. For the most part, if you're underfitting, you want to increase model capacity. If you're overfitting, you want to decrease model capacity. Some things are a little bit counterintuitive, like it can be really good to have high depth and high numbers of hidden units, but then also turn up a lot of regularization hyperparameters. So not all forms of model capacity are created equal. It seems good to have lots of parameters, but then restrict the effective capacity by using lots of regularization. In practice, we also don't usually set all the hyperparameters by hand by reasoning about them. Instead, we use some kind of search algorithm. There are various Bayesian search algorithms. For the most part, I personally haven't seen them outperform random search. So my default recommendation is still to use random search. The idea of random search is just that you define a probability distribution over reasonable values of several different hyperparameters, and you sample several of them, test them out, and then you usually run the search again after shrinking the range to be near some of the best values that you found in the first pass. After you've done 2 or 3 rounds of that, you should have an extremely competitive set of hyperparameter values. An important thing to understand is that grid search is probably not a good idea. Grid search is an algorithm that was really popular for SVMs that then some people instinctively bring to deep learning. But the problem with grid search is that you look for several different points on an evenly spaced grid. If the number of parameters you're setting is small, like 2 or 3, then that's reasonable. And that was the way that it worked with SVMs. When you're trying to set something like 40 parameters for a deep neural net that has different hyperparameters at every layer, then you really want to actually be going to random points because they get you more unique values of each hyperparameter. So in this grid, we've plotted performance as a function of one hyperparameter on the horizontal axis, and then the other hyperparameter on the vertical axis. You'll see that the vertical axis doesn't really matter all that much. That as we change this hyperparameter, the performance doesn't really change. But as we change the hyperparameter on the horizontal axis, we get this really clearly defined peak right here. Grid search actually visits the same set of 3 values for every row for this hyperparameter. So it actually completely overlooks that nice peak of good performance. Random search gets a unique value of every hyperparameter more or less every time you sample another value. I mean, I guess it's possible you could repeat some, especially if they're discrete valued, but if they're continuous valued, the probability of repeating a setting of a hyperparameter is essentially 0. And so in this case, we actually get 9 unique values of each hyperparameter, and we find a value that's very close to the peak of the horizontal hyperparameter.
Real quick, one of the streamers is asking you to go over a random search again because she couldn't quite hear.
Oh, okay, yeah, so the idea of random search is just for every hyperparameter, you specify a range of values that seem reasonable for it, and you just randomly sample several values and try them out. So for example, you might say the learning rate should be chosen by sampling a uniform value between -4 and positive, or -4 and 0, for example. And then you might take 10 to the power of that value and use it as your learning rate. And then you might also have something like the number of layers in your ResNet. And that you might make that be a random value between 1 and 5 ResNet blocks and 1 and 3 layers per block, something like that. Those can just be sampled from a uniform distribution. And then you sample 25 of these sets of hyperparameters, and you run those 25 hyperparameter sets in parallel on a cluster. So you're doing 25 experiments, but you only have to wait for the length of time that it takes to run one of them. And then you look at the results and you refine your search. So like maybe your ResNets all did really well when you have 4 blocks. So then instead of randomly sampling between 1 and 5, the next time around you randomly sample between 3 and 5 to be closer to that sweet spot of 4 and spend more of your time searching that area. And then maybe on the second round of 25, all your best results are again using 4 blocks. So then in the third round of searches, you only run 4 blocks and you use random values for the other hyperparameters. So then you really zero in on the best learning rate for the 4-block ResNets.
So why aren't, it seems like the advantages of the random hyperparameter searches should be similar to the Bayesian searches, only the Bayesian hyperparameter optimizations would have less exploration than the random search.
Well, it depends on the way that the optimization algorithm is designed and on the strength of your prior and things like that. A lot of the algorithms that people use are actually biased toward too much exploration and not enough exploitation. My main bad experience that I've had with Bayesian hyperparameter optimization algorithms is that the Gaussian process wants to explore all the corners of the space before it will start to explore the middle. And so it will propose nothing but really extreme values of all the hyperparameters. So like if I say I have something like a learning rate and I have something like a momentum value, it will end up proposing the absolute largest learning rate and the absolute largest momentum value. And then the combination of both of those together is just really unstable, and learning explodes. I get not a number of values, and it reports that test error was essentially 100% at the end of training. And so then it's like, okay, I'm going to use the absolute smallest learning rate and the absolute smallest momentum value, and then it learns until it runs out of time, and it didn't go anywhere because it used the smallest version of both. And then the test error is essentially 100%, and so it's basically just done 2 different trials where it did as badly as possible, and it hasn't extracted any signal yet. A lot of the time with algorithms like that, I've even found that I can seed the database of the meta optimization learning algorithm with examples that I came up with by hand, and it will choose to ignore those values and keep exploring the corners of the space. So if you have very few hyperparameters and there aren't that many corners, you'll eventually just enumerate them all and keep going and start to do really well. If you have like dozens of hyperparameters, then you're just exploring this exponential hypercube, and there's no way that you're ever going to get through it, even with a really big cluster. And in cases like that, I generally fall back to random search. Yeah.
So there was this paper, learning to learn by gradient descent, trying, I'm guessing it. So is it better than random search of hyperparameters, or?
So learning to learn by gradient descent, I think was more or less trying to like invent a new learning rule, if I remember correctly. I don't remember it off the top of my head especially well. But that was, if I remember right, it was trying to figure out what kind of actual update step you should be doing. You know, should it look more like Atom, or should it look more like SGD with momentum? There's another paper that's related to what you're thinking of. I think it's called like Hyperparameter Optimization by Reversible Gradient Descent. And that's about actually backpropagating through the entire learning process to get a derivative with respect to the hyperparameters. The issue with that approach is just that it doesn't really scale. The other thing is, if you look at this curve for the learning rate, if the learning rate is too small, you basically always know to increase it. It doesn't take a derivative to tell you that. And then if it gets to be too big, here it's plotted as just being a very straight line because this is a really clean example. But if you look at what happens with the reversible gradient descent approach, you get like a really jagged line where, because of that sawtoothing pattern, the derivative is almost as likely to point in the wrong direction as to point in the right direction. So it doesn't really help you that much when the learning rate is too small because it's too obvious to know what to do to fix it. And it doesn't even really tell you when the learning rate has become too big, because when the learning rate is too big, your derivative doesn't mean anything anymore.
So basically, random search is kind of doing one iteration and then hill climbing, or
well,
just resampling.
it's only really hill climbing if you have like a post-processing step where you refine the search based on the results of the first one. Yeah, but yeah, random search is not using any kind of gradient information or anything like that. So that's the hyperparameter search is actually the end of my slides. So I'm free if you have questions about practical methodology in general.
Hey, could you talk a bit related to initialization? Like initialize. Why one method over the other is already launched?
Yeah, so batch norm has more or less fixed the optimization problem. You just build it into your architecture that you subtract the mean and divide by the standard deviation for each of the units. And you can more or less forget about looking for a good initialization now. If you don't want to use batch normalization for some reason, then a very good approach is to use data-based initialization, where you just set the bias parameters and set the scale of the weights to do the same thing as batch norm when you first start the learning process, and that will continue to work very well. There's a few other procedures that can be helpful if you want to go to like very, very deep networks, where you actually try to look at the magnitude of the gradients and things like that. David Cicillo has a paper called Random Walk Initialization, where he describes how to train networks that are 1,000 layers deep without batch norm. But usually there's not much of a reason that you would need to spend that much time thinking about initialization. You just use batch norm and forget about it. This used to be a more important topic before batch normalization existed and became as standard as it is today. Yeah.
One of the stream watchers is asking if you don't have a very large data set and data augmentation doesn't solve it, what else can you do to reduce test error? In this case, he's already using dropout and L2 norm, and it's an image data set as well.
Well, you could try switching to a Bayesian method. If you look at a lot of the head-to-head comparisons of different models on really small data sets, like the alternative splicing data set. In the really low label regime, Bayesian neural networks actually beat the more common backprop-based deep learning methods that just optimize the likelihood. And it's also just kind of a research frontier to do better in those settings.
Gotcha. And are there any like example papers or projects that he could look to real quick, like off the top of your head that you know of?
I guess if you look in the chapter, I think it mentions this fact and mentions the alternative splicing data set. If you read that paper, it describes the models that they ran, and you could just look up the best models on those very small data sets and try to re-implement those. Another thing you can do is semi-supervised or transfer learning. So if you have a lot of unlabeled examples but not very many labels, or if you have a lot of labels for another task, you can use something like unsupervised pre-training or generative adversarial networks that have multi-class discriminator. In the paper, Improved Techniques for Training Generative Adversarial Networks, we showed how to get really good semi-supervised learning performance on MNIST and CFAR and Street View house numbers. So that's a case where we're artificially restricting the number of labels we have, but it might work on other tasks as well.
Another question from
Yeah.
Pedro. It is well known that increasing depth helps regularizing the network, increases training error, and reduces test error. Why aren't really deep, fully connected networks, 20 plus layers, used then?
They usually just aren't that necessary. I guess the main case where people have worked on really complicated tasks where the depth has become an important competitive factor is object recognition, and that's not really fully connected. There aren't really that many tasks where fully connected networks are that interesting. Most things you end up going either convolutional or recurrent when you start to scale to really interesting problem sizes. So there's not really much of anything that I can think of off the top of my head where scaling isn't so important that you move out of the fully connected model architecture, and where the data is complicated enough that you need a lot of depth. Yeah.
Would you recommend toy problems or some good Kaggle competitions for a beginner to kind of get used to more practical applications?
Well, if you want to learn reinforcement learning, you could check out OpenAI Gym. If you want to just work with like very toy machine learning problems, MNIST is kind of the traditional first thing that people try. If you have a good GPU, it's honestly not all that hard to run ImageNet experiments these days. Like the amount of time it takes to run an experiment on ImageNet now is more or less the same as the amount of time it took me to run experiments on MNIST when I started my machine learning career. So even ImageNet is not really that bad of a playground now.
So Kaggle is not.
Well, so Kaggle, it's hard to recommend a good contest just because there's different contests always running, and I don't know off the top of my head what's running right now. Kaggle is a good thing to do, but just because it's going to be a different experience every time, it's maybe not going to be the sort of thing where people can help you quite as much as if you start working on MNIST and you have some kind of beginner question about MNIST.
Jeremy might have a good answer for you. Please get some questions as well. Peng Cheng is asking, is there like a general rule of thumb for how many random searches should be done for hyperparameter searching?
Oh, well, it depends on the size of your cluster and things like that. If you have enough computers that, like 25 or so is not going to make your coworkers angry at you, then usually there's kind of diminishing marginal utility after like 25 experiments or so, and you're better off just running those and then tightening the search before you run the next 25. But these are just sort of rules of thumb. They obviously depend a lot on the exact number of hyperparameters you have and on how the performance of your task how complicated a function of the hyperparameters it is. So when I say something like 25, that's sort of reflecting something about the number of hyperparameters I usually use, and also how hard it is to find good ones within that set.
Question. Try to understand a little bit more to the extent you can share on the Google image problem. I'm assuming that the data set didn't exist prior to this work, so someone actually generated the data set and there was effort in labeling it to get it to the large enough size that it needed to be trained on. So are there any strategies in terms of the chair where they kind of, because to me that seems like a huge task, because you can't just use humans for all of that. That's a large number of images.
Okay, so some of it was just people who were paid to label them. Google built a system that's kind of like Amazon Mechanical Turk, but specifically for Google to use. And we published the names of all of our employee labelers.
Okay.
And there were a lot of them. Like, I haven't actually been to the building where they work, but evidently a lot of them commute by taxi, and there are like big traffic jams of taxis going to the building.
Wow.
So that was quite a lot of human labeler time, just for people paid to sit there labeling things all day. But also there was reCAPTCHA used, Street View address numbers, to crowdsource transcriptions for free. That people would be shown 2 transcriptions, and one of them already had a known value so that you could tell if they were faking it, and the other one was not already known, so whatever they entered would be added to the database.
You could experiment with the image quality and things like that to kind of create your augmented data set as well, like slightly blurry, not that blurry.
Oh, like to see if people had trouble labeling it when it was blurry? Or
Right. I mean, was it?
I don't know of a lot of experiments with that particular aspect of it.
Because when you generate the initial data set, do you normally recommend spending any time trying to figure out, I mean, it's hard enough to just get the data, but is there any thought, like large companies, is there any thought in terms of some weak or strong prior in terms of we're going to try these different variations of.
Oh, like what resolution it should be prepared at and things like that. A lot of the time that's driven by just looking at the data and judging for yourself how hard it is to process, and also trying to keep the computational costs down. So usually you choose an input size that's relatively small, relatively low resolution, so that it doesn't cost as much electricity to process.
Right.
And you try to get it to the point where the task is doable, but you don't think you're losing too much performance from the low resolution.
So in terms of image generation, I'm just making a wild guess, like you have your Google Cloud running, it's just taking pictures different times of the day maybe, or what have you. So there's not like, you're not putting too much strong prior into, I want to make sure I get some for morning light, dusk. I mean, depending on what you're doing with the image data, of course, but.
I don't know that much about the car driving schedule, and that part was probably a lot less coordinated with the address number task than some of the other things that I did. Another thing is just, you try to store as much as you can so that you can change decisions later, right? Like, if you store the high-res images of all the address numbers, then you can always reverse a decision about which resolution you want to use with the machine learning model.
But some of these tasks, you said you want them to be like AI and close enough to human experience, and then human experience is such a big continuum, you can't always get enough examples of all of them. So
Yeah.
I was curious if they had any good tactics for that.
Oh, yeah, I mean, that part is not really that scientific so far. That's just sort of the engineers on the project using their judgment and a bit of trial and error.
Looking back on your first internship with Google, or I think actually your only internship, is there something you would do differently now, or were there any like common pitfalls that you like ran into while there that you didn't already mention in the slides?
Not really. I mean, that internship went really well.
Okay.
I guess I could describe a little bit of like why it went well for things that were not machine learning reasons.
Sure.
So one thing is when you're choosing where you should work, you should think partly about where you can have the most impact, rather than necessarily where the people that you look up to already are. So when I did that internship, I had the choice of going to the brain team, where a lot of people that I already respected a lot from grad school were, or going to the Street View team, where they knew that they needed machine learning and they were already making some effort to use it, but the people working on it didn't have nearly as much experience. And because I chose to go there, that meant that the marginal value of having someone who'd done a PhD in machine learning was a lot higher than if I was like the 30th person on the team that had done a PhD in machine learning. I guess another thing is thinking about the skills that a team has and making sure the project is really uniquely suited to that team. So Street View was a really great environment because there were people with lots of different skills there. There were people that were good at databases, people that were good at photography, people that were good at machine learning, and all kinds of numerical programming stuff. And that meant that we could tackle this kind of interdisciplinary problem where we really had to build the data set and everything. If you were in like an academic machine learning lab, then you could have done the machine learning really easily and probably done something fancier on the algorithmic side. But it would have been really, really hard to do all of the other kinds of work that went into making the project a success. And then I guess the last thing is just finding something that really unites a lot of people's interests. So this was compelling from a research point of view because we were getting neural networks to do end-to-end tasks that had a lot more complexity than the tasks they'd done before. That they had to deal with like a whole sequence of things in an image. So it was interesting to me as a researcher, but it also had like a really obvious and immediate business use case. So when you can find things that really fit the team well, really fit everybody's incentives and goals well, and where you are providing something kind of unique to the team, that's when you can make a really big impact. A lot of the time, you think about like, oh, I should work really hard and be really creative and stuff like that. I mean, that's true too, but you're usually kind of fighting an uphill battle to do that. And if you can just be in the right environment to use the skills you already have, then you can have much more of an impact even if you have just like the same level of creativity that you have in a normal work day.
That's fair.
Could you tell a bit about the focus of OpenAI? It seems from the website that the gym has a lot of reinforcement learning types of things. So is that the general?
Yeah, so GEM is specifically for reinforcement learning, and reinforcement learning is one of the main things that's studied in OpenAI. We try to focus on aspects of machine learning that are not anywhere near solved yet. So for example, we're not competing in object recognition or anything like that. Instead, we're focusing on generative models, semi-supervised learning, reinforcement learning, being able to analyze models and determine whether they're safe, that kind of thing. There's a lot of other labs that focus on more of the application-driven stuff and really perfecting the tasks that we can already do more or less correctly.
What are the top application of like real life application of reinforcement learning?
Well, robotics is one that can be really important, and that's what we concentrate on. Reinforcement learning is used for other things, like finance, making trading decisions, and also Google was in the news recently because DeepMind's reinforcement learning algorithms are now used for optimizing various aspects of the data centers. And they said that they've actually reduced Google's energy costs enough to justify the price of the DeepMind acquisition, which was rumored to be something like 400 million pounds. So it seems like reinforcement learning is working very well for improving energy efficiency and cooling. I don't know enough about data centers to tell you exactly which actions it's controlling.
Any more questions?
Of the unsolved problems you're working on, where do you feel like you've made the most progress and maybe like the least progress?
I don't follow the reinforcement learning well enough to really judge. Of the topics that I'm working on myself, I feel like probably the most important thing that we've done so far is Tim's feature matching generative adversarial nets for semi-supervised learning. But we actually developed something that I've felt like using in other projects where the goal was not to do semi-supervised learning. There was just another project where I had to do very well with few labels because it was expensive to get labels. And I thought, oh, I know, I'll use Tim's code. And it actually paid off and worked. The other aspect of generative modeling where we actually want to make really good high quality samples, like imaginary images that have never been seen before. That's much harder, and we're making less progress there. We are also making progress there. In the last 6 months, we've moved from not really being able to make large images at all to being able to make large images that have object parts, but not the right assembly of objects overall with the right 3D composition. But we're not really to the point where you would actually want to use our image generators yet for anything else.
Any work from other labs that you're particularly excited about?
I've been really excited about IGAN. It's an interactive generative adversarial net for assisted artwork. It's coming from Berkeley and a collaboration with Adobe. And it was the third most popular trending repository on GitHub today. And the basic idea is that you can draw like a black triangle and a few wavy green lines, and it will use a generative model to search for an image that looks photorealistic but is close to what you drew. So it'll turn your little triangle into a mountain and turn your little wavy green lines into a field.
Any more questions? Okay, well, that concludes everything.
Oh, there's one more question.
One more? Yeah, go ahead.
Have you seen applications in the software industry, so like code reviews or automatic code reviews or
I think OpenAI releases a thing called requests for research, where we suggest things people should do. I think one of ours is to make an LSTM that will read GitHub pull requests and predict what changes were made in the review process, so that you could then plug that into your editor and it would automatically suggest changes for you as you type. If we haven't posted that in our request for research, it should be in there. I don't know of anybody actually doing that yet. There is some stuff based on analyzing code for security flaws, or actually designing code that avoids malware detectors using machine learning. I spend maybe about a third of my time working on machine learning security, and one of my collaborators that I've worked with a lot there is Nicholas Paperno at Pennsylvania State University. He's a co-author with Catherine Gross at University of Saarland, I think, on a paper where they showed how to basically just edit the manifest file of an Android app in order to confuse a machine learning classifier that detects malware. And just by putting spurious patterns that the classifier likes in the manifest.xml file, they were able to get malware passed off as valid code.
So, excuse me. For the malware aspects of things, I see a lot of companies saying that they're going to machine learning for detection, like maybe vector networks and stuff. And I'm just trying to get an angle as to how they're implementing machine learning to detect malware. what methods are they using?
Well, a lot of them don't really say anything about what they're doing.
Right, I mean, it's the placement of, say, info analytics and, node strings type of thing, right?
Yeah, oh, and I guess I should be repeating the question. So the question was, there's a lot of companies that say they're using machine learning to detect malware. What are they actually doing? Academic papers do things like learn the weights associated with hand-coded features. So it's not even really that strong of a machine learning approach. It's more of just a little bit of machine learning in the post-processing for how much to weight different features. You can also do things like just differentiate through sequence models that actually just read raw bytes. And you need to have a big data set for that to work very well, but it can. You can do things like data set augmentation, where you have code gen that just makes several different versions of the same program by doing synonymous rewrites of it, so you can get a big data set that way. And there's also malware detectors that are based on monitoring the activity of a program while it's actually executing. And I don't know exactly which kinds of activities it looks for, but the idea is you can find signs of malicious behavior based on what actually happens at runtime.
All right, final questions, any? All right, that concludes tonight. Thanks for coming out.
Let's go.